Hello everyone, this is the linear least squares assignment introduction section. So today I'm going to talk about the least squares assignment and talk a little bit about how to go about solving it. So this assignment is putting you in the shoes of someone who works with robots, which is cool. And you're trying to program a robot to move back and forth the way you want it to. So you have a robot that can move in one direction, so along, say, the x-axis, or whichever your favorite axis is, it moves along that axis only in directions positive and backwards, or forward and backwards. And at each time, and it moves one time step at a time. So in each time step, there is a force applied to it, and that force changes from one time step to the next, but it does not change within the time step. Basic physics will give us the relationship between the force, which we call u, the velocity, which we call v, and the position we call p. Now that is given for you in equation 1 of the assignment PDF. So we're going to use a variable called x, which we have, for which we use both p and v. So we call x the state of the robot, which is both its position and velocity. And equation 2 is what gives you to describe that. So to solve these problems, we're going to use the definitions that are given to us for C and D, the matrices. And then we're going to use the equations that are given right below those definitions. And that is going to give us what we need to write the code for the functions that we need. So the first function you need to write is comp input. Now, this problem, at first, it looks really complicated just because you have to read through 2 whole pages of text and equations just before you even get to the assignment. But once you get through the math and the physics, it's really not that hard to code up because it's just a few simple steps once you manipulate the equations you need to, or in the way you need to. So what we're doing in this function is we're given the initial and desired final state of the robot. So we know the location and the velocity at the beginning. We know the mass of the robot. We know how many time steps there are, as well as what is the length of each time step. So with all of those things, as well as the initial position and velocity, we know what we want to be the final position and velocity. What we're trying to do is determine what force U is necessary at each time step along the way to bring it to the desired final one. Now, it's also worth noting that there are many, if not infinity, possible combinations of U0, U1, all the way up to UN-1 that will achieve this result. Especially since we open up the door for forces in the negative direction, we could have, up to an infinite possible combinations of forces in each time step that would give us the desired outcome, which is the final position and velocity specified by the input arguments PF and VF. However, there are 2 specific ones that we're looking for. And those are the one that has the minimum number of non-zero elements, which is what we get from the command \, and we're looking for the one that has the smallest possible norm, which we use pinv. So for this problem specifically, we're going to focus on the equation xn equals c to the n times x naught plus c to the n minus 1 times d times u naught, and so on down the line up to c to the 0 times d times u to the u of n minus 1. In this equation, you're going to want to pay attention to the dimensions of every single term. Note that x is 2 by 1, as well as c being 2 by 2 and d being 2 by 1. So also just think to yourselves for a moment about what would be the size of c to the n times x naught, as well as every term that involves a c raised to some exponent times d. So given this equation, which is just a slightly rewritten, a slight change of notation from the one at the very bottom of the page 2 on the PDF, we're going to start with this, and then what we're going to do is we want to manipulate this equation so that all the terms we know, aka which ones don't contain a u, are on one side of the equation. And then after we do that, we work towards putting the equation into the form AU equals B, where A is a 2 by n matrix, B is a 2 by 1 array. Now, where n is n steps. So A is going to be a 2 by n matrix, which we're going to multiply by the array U, which contains u naught, u1, etc., up to u n steps minus 1. Now, u is what we're solving for because it is what is unknown up to this point. And keep in mind, up until now, everything we've been doing is something you would do on pencil and paper, whereas not coding this up, because this is just analytical mathematics. We're taking some equations and we're reworking them into a form that MATLAB can solve quite easily and simply. So it's a little bit of pencil and paper work, but once you get there, once you get the equations into this form, then we'll be ready to start coding, and it won't be that hard once we get there. So once we've worked the equation into the form we want into AU equals B, we're ready to start coding. And we want to construct C and D, which are simple. They're given to you in the assignment PDF, what they are. And from there, after we have C and D done, then we can define the matrix A for our system AU equals B. Now, once again, this is just coming from that equation that I just typed out for you, with the xn, etc. So this is a critical step, and this is where, for constructing matrix A, there's probably a few different ways to do it. When I did it, I was able to do it with a simple single for loop. So that's the matrix A. And then, of course, B is your known values, which would be on the opposite side of the U terms. So then, once you have A and B defined, you're ready to solve for U. And there are two ways to do this, both / and pinv. And in this function, we want to use both of them and assign one of them to U1 and one of them to U2. Because, solving the system AU equals B for U, We can solve it using both backslash, and that'll give us one result for you. And we can also solve it using pinv, and that will give you a different result for you. So you're going to want to use both of them, and then assign one to U1 and one to U2. And that one, and U1 is the one we use the backslash operator, and U2 is the one we use pinv. And after we've assigned U1 and U2, then that's basically the end of this function. The next, so all in all, this function took me less than 15 lines to do, so it shouldn't be too hard. And most of them are just defining variables. So it's not a super complicated function once you work through the math and the physics and get this into a system of equations that you can understand. So the majority of your work will probably be on with the pencil and paper, and then once you have that done, the coding should hopefully not be too complicated. Yeah, so that's that function. And then the next function is SimRobot, which, believe it or not, is even simpler than the first one. So before, in the first function, we were given an initial state and a final state, as well as the other necessary parameters, including time steps and mass, etc. In this function, in the first function, we were given all the parameters as well as the initial and final states of the robot. Now, in this one, we are given the parameters of mass and time, and we are given the initial state, so the initial position and the initial velocity, and we are also given the array u. So we now, whereas in the previous one we were determining u, the force, at every time step, in this one we're given u, or the force, at every time step. And what we want to calculate is the position and the velocity at every single time step, given that force. So for this one, it's going to be very similar in terms of the equations we're using, as well as the fact that we are combining position and velocity into a single variable v, using making it into a 2x1 vector. So because of that, we still define the matrices C and D the same way as we did in the first problem. And in this in this case, where so in the previous one we wanted to solve all of the time steps simultaneously in order to solve for all of the u's simultaneously. In this one, we don't even need to do that. We want to pay close attention to equation 3, which gives a simple relationship between x at the k plus 1th time step and x at the kth time step and u at the kth time step. So once again, that's probably just going to be a very simple for loop you use to do that. And this is just, and remember, this is not solving a system simultaneously. This is just computing iteratively. We're given the position at initially, as well as the force at every time step. So for every time step, we use the state from the previous time step as well as the force from the previous time step to determine the state at the current time step. And then once we compute that, we will have most likely a 2 by something array, which will have, which is the state, which has both the position and velocity. And from there, we can just extract the position and velocity from that matrix. And your hint is, what is the definition of x? So that's given in the assignment sheet. So we just have position on top of velocity. So it shouldn't be hard, hopefully, to extract the position and velocity from that. And after that, we're pretty much done with these two functions. So on page 5 is given to you some code that shows you how you should be able to run these functions, and you should be able to make some plots using the position and velocity and force values given. I guess the position and velocity and the mass are given, but then you calculate the force, and then you simulate what happens to the robot based on those force values. So that's about the end of what I had prepared. Does anyone have any questions? Is anything still confusing to you about what I said, or something I wrote or typed or anything? Or does this all make sense to you guys now? I guess. So if there's no questions, then I'll go ahead and stop the recording, and wish you the best of luck on this assignment. This is a fun one, so hopefully it won't be too difficult. And of course, if you have any questions, don't hesitate to come by the lab session.